So there's another way of proceeding, which is what you might have thought. Hey, look, we got two complex roots. That gives us two solutions, which are different. They're not, neither one is a constant multiple of the other. Why not? So the other approach is use as the general solution y equals, now I'm going to put a capital C here. You'll see why in just a second, times e to the a plus bi times t. And then I'll use the other solution, C2 times e to the a minus bit. These are two independent solutions, and therefore, can't I get the general solution in that form? Now, in a sense, you can. The whole problem is the following, of course, that I'm only interested in real solutions. This is a complex function. This is another complex function. It's got an I in it, in other words, when I write it out as u plus iv. If I expect to be able to get a real solution out of that, that means I have to allow these coefficients to be complex numbers and not real numbers. So in other words, what I'm saying is that an expression like this, where the a plus bi and a minus bi are the roots of that, are complex roots of that characteristic equation, is formally a very general complex solution to the equation. And therefore, the problem becomes, how from this expression do I get the real solutions? So the problem is, I accept these as the complex solutions. My problem is to find among all these guys where C1 and C2 are allowed to be complex. The problem is which of the green solutions are real. Now, there are many ways of getting the answer. There's a super hack way. The super hack way is to say, well, this one is C1 plus ID1. This is C2 plus ID2. And I'll write all this out in terms of what it is, you know, cosine plus sine, cosine plus I sine, and don't forget the e to the at. And I'll write it all out, and it'll take an entire board. And then I'll just see what the condition is. I'll write its real part and its an imaginary part. And then I'll say the imaginary part has got to be 0. And then I'll see what it's like. That works fine. It just takes too much space. And also, it doesn't teach you a few things that I think you should know. So I'm going to give another. So let's say we can answer this two ways by hack. In other words, multiply everything out. Multiply all out. Make the imaginary part equal 0. Now, here's a better way, in my opinion. What I'm trying to do is, this is some complex function, u plus iv. How do I know when a complex function is real? I want this to be real. Well, the hack method corresponds to saying v must be equal to 0. It's real if v is 0. So expand it out and see when v is 0. There's a slightly more subtle method, which is to change I to minus I. And what? And see if it stays the same. And see if it stays the same. Because if I change I to minus I, and it turns out the expression doesn't change, then it must have been real. See that? V must have been 0 if this expression doesn't change when I change I to minus I. Well, sure, but, well, you'll see it work. All right, now that's what I'm going to apply to this. If I want this to be real, I phrase the question, I rephrase the question for the green equation, the green solution, as change. So I'm going to change I to minus I in the green. thing. And that's going to give me what conditions, and that will give conditions on the C's. Well, let's do it. In fact, it's easier done than talked about. Let's take the green solution and change. So I don't want to, well, I better recopy it. C1. So these are complex numbers. That's why I wrote them as capital letters, because little letters you tend to interpret as real numbers. So C1, e to the a plus bit, I'll recopy it quickly, plus C2, e to the a minus bit. Okay, we're going to change I to negative I. Now, here's a complex number. What happens to it when you change I to negative I? You change it into its class? What do we change it into? Its complex conjugate, right? And the notation for complex conjugate is you put a bar over it. So in other words, when I do that, the C1 changes to C1 bar, complex conjugate, the complex conjugate of C1. What happens to this guy? This guy changes to this guy changes to e to the a minus bit. This changes to the complex conjugate of C2, now times e to the a plus bit. Well, I want these two to be the same. I want the two expressions the same. Why do I want them the same? Because if they stay, if there's no change, that will mean that it's real. Now, when is that going to happen? That happens if, well, here is this, that, if C2 should be equal to C1 bar. That's only one condition. There's another condition. C2 bar should equal C1. So I get two conditions, but there's really only one condition there, because if this is true, that's true too. I simply put bars over both things, and you know, two bars cancel each other out. If you take the complex conjugate and do it again, you get back where you started with. Change I to minus I, and then I to minus I again. Well, never mind. Anyway, these are the same. This equation doesn't say anything that the first one didn't say already. So this one is redundant. And our conclusion is, that the real solution to the equation are, in their entirety, I now don't need both C2 and C1. One of them will do. And since I'm going to write it out as a complex number, I'll write it out in terms of its coefficient. So it's C1, well, let's just simply write it. C plus I times D. That's the coefficient. That's what I called C1 before. And that's times e to the a plus bit. There's no reason why I put bi here and id there, in case you're wondering. Sheer caprice. And what's the other term? Now the other term is completely determined. Its coefficients must be c minus id times e to the a minus bit. In other words, this thing is perfectly general. Any complex number times that first root you used, exponentiated. And the second term can be described as the complex conjugate of the first. The coefficient is the complex conjugate, and this part is the complex conjugate of that. Now, it's in this form, many engineers write the solution this way, and physicists too. So scientists and engineers will include. Write the solution this way. Write the real solutions this way in that complex form. Well, why do they do something so perverse? You'll have to ask them. But in fact, when we study Fourier series, we'll probably have to do that at one point. If you work a lot with complex numbers, it turns out to be, in some ways, a more convenient representation than the one I've given you in terms of sines and cosines.